Nearly every task management system has some concept of repeating tasks. It's what elevates them above a dumb list that you could just write in a word processing program or something. The difficulty is getting repeating tasks just right is really difficult. For a start, it makes the users have to think too hard about exactly what they're going to need up ahead of time. There's some types of repeating tasks that have a really obvious cadence, such as I need to do my taxes every calendar year. But there's plenty of others that don't. For example, when do I need to buy shampoo? I don't know, it's probably every couple of months, but I haven't actually measured it. We have a task management system that is overseeing all your tasks. Why can't it work out exactly when you need to do things? Deluge's smart repeat system lets you put a repeating task into Deluge without needing to know exactly how often you want it to repeat. And Deluge's review process will help you to get that right. It will ask you questions. Does this need to be done now? And you can answer yes or no. And if you answer yes, it'll put a task on your list, which you can then complete whenever you get around to it. And if you answer no, then it's not appropriate to put the task on the list yet. Deluge learns from both of these answers, and over time it will get a better and better estimate of how often this particular task needs to be done. So how does Deluge accomplish this learning? Let's have a look at precisely what we're modelling here. Suppose we've got time going along and at some point we've got a task that needs to be done. Let's continue with the example of buying shampoo. So suppose I buy shampoo just here. This is when I actually did it. So what that means is presumably this was on my to-do list for a little bit before then, because unless I'm very, very diligent, I'm not going to get to actually doing a task on my to-do list the same day I put it there. And then, could I buy shampoo again the next day? Well, there wouldn't really be any point in doing so. So let's say the answer is no. It doesn't make sense to buy shampoo the day after you've just bought some. When does it make sense to buy shampoo again? Let's say it makes sense over here. So this is when it makes sense to buy shampoo. So the task could be done. Let's say it needs to be done. This doesn't mean that this is actually the point you've run out of shampoo. It would be a bit silly to wait until you've run out before buying some more, because then in the time it takes you to get to the shops, you will not be able to wash your hair. So let's put at the end here, this is where we buy some the next time. So what we've done is we've bought shampoo over here. We've waited until we needed to buy it again, which is when we're nearly running out. Put it on our list, and then soon after that, we've bought some more. And this point that's marked needs, this is when it makes sense to buy shampoo. This is the point at which, before this, you'd just be stacking up bottles of shampoo that you don't need. But after this time, you're buying some in preparation for the bottle that's nearly run out. Of course, you may be a more or less diligent person, and so therefore this gap may be longer or shorter. That's up to you, how you manage your own life. But the crucial thing is, what we want to model is this gap here. This is the length of time from when you do the task to when you could do it again. And I'm going to call that the cadence. If the user already knew what the value of this cadence was, they could just use a regular scheduled repeating task. But if they don't, then they can ask Deluge to learn it for them by creating a smart repeat. So how does Deluge learn that? We're going to learn it by looking at what the user actually does and also how they answer our review questions. So our review questions are forced choice. They are, does this need to be done? The user can say yes or no. And it's up to us, it's up to the app, to choose when to ask those review questions to the user. So they're sort of forced choice. I mean, the user can always skip review questions if they actually don't know the answer. But let's assume the user is going to answer the question. But they're only going to record data on the days that we actually ask the question. If we asked the review question every day to the user, do you need to buy shampoo? We would get a very, very accurate answer, but it would be exhausting. The user would soon quit using the app because they would be being hassled by hundreds of questions every day. So the problem is here, we've got this trade-off between bothering the user too much and not really getting any useful information to learn from. There are a few other things that are going to go into this system besides just the answers to the review questions, and one of which is when does the user actually complete the task? So in our example, this tells us when the user actually bought shampoo. We don't want a review question for this because we can track when the user actually ticks the task off on their to-do list. In Deluge, there are many ways to actually mark a task as complete, and we want all of these to feed into the system that's tracking things for the purpose of Smart Repeat. So Deluge's backend and all of its business logic is written in SQL. And what we're doing here is we're using a trigger to check whenever the status is changed. So status is a field on the tasks table. Whenever that is changed to completed, then we call this function. And we have quite a bit of complicated logic as part of this, which actually is triggering our computational model to predict when the next time the user will need to be reminded about this is. And for the rest of this video, what I'm going to be going through is exactly what it means to use a computational model to make a prediction. So you can see here on this line, we're calling this other function to run our model. And after that, we've got some estimated times the user might next need to be reminded about the task. But let's take a step back from the code and go back to talking conceptually. Before we even get on to talking about how we can use our data to make predictions, let's talk a little bit about how I'm actually saving the data. I could just make a log table that logs all the sort of events that are related to this particular repeating task. So you might have an event for when a task is completed, you might have an event for when the user answers a review question, that kind of thing. And the problem with doing it that way is that data could be very messy. There are many, many ways that the user could do things out of order. For example, they might just go and buy shampoo anyway without putting it through Deluge, and that way there isn't really a good answer they can give to a review question. Or they might do things like take the task that Deluge has created for them and delete it rather than completing it, or maybe put it on hold and do anything that is out of our sort of expected behaviour of a user. And that makes the data really messy. So one way I'm slightly mitigating this is I'm actually storing this log data in what I'm calling history pairs. History pairs represent the gap between the point at which the task is complete and the point at which the task needs doing again. They represent the thing we're actually trying to predict. And so each history pair stores the date where this happens, and it stores the date that this happens. So historical history pairs have both of these dates put in, but the most recent one, if, for example, the time now is just here, then the most recent history pair will have the start date in it, but it won't have the end date. And when the user goes to do a certain event, we look for the most recent history pair and amend it with the end data to fill in the other part of it. This way of storing data means that our data table can never get too out of sync with what we actually need for predictions, and it forces us, when developing the code, to actually take into account like all the different possibilities. What if the user does this when there is an active history pair? What if the user does this when there isn't? Every one of these circumstances has to be taken into account. So you might be asking, why are we storing all this history at all? Why don't we just store a running average? There's essentially two main reasons. One of them is, what if we want to change which model we're using in the future, or guard against data loss, make sure that our code isn't making some bad assumption and mucking up the numeric value. These are good enough reasons on their own. The other reason is there's actually some mathematical reasons why storing things in this way mean that we can finely tune a computational model, and I'll get to that later. So this whole process is talking about when we need to ask the user if they need to do a task. If we knew absolutely everything, the best time to ask the user if they need to do a task is just as they're starting to need to do it. To the user, if we ask them before they need to do the task, that's just noise. That's a useless question to them. And if we ask them too late after they need to do it, then the app is not being very successful in actually prompting them. They might already have run out of shampoo and be getting really frustrated. We want to ask earlier, but not so early they don't need to do it yet. To be able to predict that, we need good data. And we're making quite a lot of assumptions that the cadence of any individual task stays pretty similar over time. But there's not much we can do about it if it doesn't, really. Asking a question before the user needs to do the task, asking the user a review question like, do you need to buy shampoo? And the user answering, no, I don't. That's not a very heavyweight interaction for the user. So while we do want to minimise how often we ask them earlier, it's not the end of the world if we do that once in a while. And indeed, we actually need to be able to do that to help our learning process. Because if all the data we're collecting is the answer to this review question, do you need to do this? If the user answers yes, we can't distinguish between, hey, we asked them at the actual ideal correct time, or we asked them way too late. Both of those would be the answer yes to that question. We could add some mitigations to that by adding more responses the user could make. For example, one we are going to add is, I did this recently, for if the user had decided on their own volition they needed to buy shampoo and gone and bought some. That's a way that when Deluge asked the review question, the user could answer that without just saying, well, no, I don't need to buy some. And that would go into the training and help Deluge to get it right next time. But the more of these options that we add, the more cognitive load there is to the user when they're answering a review question. So we can't just add as many situations as we can possibly think of. So what if we're way off and the user just goes ahead and does it? And we're so far out that we don't even ask the review question for quite a while afterwards. The user isn't going to click, I did it recently, because it's not even very recent. Well, the ideal is that the user would go in and tell Deluge that they've gone and done a tracked task unprompted. There'll be a little action in the context menu on a task. But that's a lot of burden to put on the user. This is something that I'm actually going to have to think about. This isn't one I've got a perfect answer to yet. So when the user completes the task, how long do we wait before asking our review question? That is the value that we're modelling. So we're modelling the ideal time before asking the review question. We take the latest result of the model and we wait that long before asking. But what if they say no? So going back to our diagram, suppose that we ask the user if they need to buy shampoo at this point, and they say no. In order to do that, we would have had to have had our cadence be this long, because that's why we asked them then. And they've said no. So how long do we wait? We don't want to wait the same length as the cadence again, because that would be up to here. And we know that the user is actually going to need to buy shampoo at this point. So what we need is a smaller back off for if they said no, not yet. And again, that would be the ideal amount. So our model is going to have to give us two values. One possible value out of the model is what's the back off after the user's done the task. That should be a sort of longer value. And then we need a shorter value for what if we ask the question to the user and they say no. How long before we ask again. And like before, the safest option is to err on the side of a shorter time, because that way we don't miss the actual point that we need. But if the time that we predict is too short, then we'll be asking the user the same question multiple times. That will give them question fatigue. That will make the app a lot less useful for them. So let's finally talk about how we actually model some of this stuff. As I alluded to before, the modelled value is actually pretty similar to just an average of the time between the user doing the task and the user next saying, yes, I need to do it again. We're storing history. We could easily compute an average of those values for all the historical data that we have. But it actually helps to think about this in computational modelling terms. So now I'm going to introduce the Bayesian gamma exponential model. And for those of you without a mathematical background, that's probably a load of scary words. You probably think it's really complicated. Actually, it's not that complicated and it's not that dissimilar to storing a running average. but I will explain a little bit about it. So if we weren't actually storing history, but we were just storing some model values that we were going to update, the values that we would store are called alpha and beta. And alpha, at its simplest, is the number of events that we've observed. And beta is the sum of the durations for those events. And you'll probably have noticed that if we wanted to compute the average duration, then it is quite simply beta over alpha. So we could just store those two values, and then every time we get a new piece of data, we add 1 to alpha, we add the duration to beta, and that's enough. So we don't actually have to store all the history in order to use a computational model. We could just do this. As I mentioned before, there are other reasons that I prefer storing the actual history, not least of which, if I change the computational model or improve it in the future, I can go back and recalculate everything. As it happens, the way Deluge's modelling works is we recalculate everything from the history every time we need a model value. This actually takes hardly any time at all. It's not like we're working with millions and millions of data points here. We're more likely to be working with a very small number, and therefore there's no computational overhead to just recalculating things each time. So looking at alpha and beta in this model with the complicated title, is it actually better to think about things this way rather than just thinking of this as a way to calculate an average? Well, yes, it is. And part of that is that other clever people have done a whole bunch of maths to work out various things that we can derive from these values and what that means. So before I go into that, I want to talk about what actually is a distribution. So we're now about to talk in terms of probabilities of things. What we're doing here is making predictions, and so probabilities, what's the chance of this event occurring after this amount of time, that kind of thing. These are the kinds of questions we actually want to ask. And so a distribution is essentially showing where all the probabilities are clustered for whatever it is you're modelling. So let's give ourselves a couple of axes. We've got time going across because we're modelling things that are related to time here. And we've got P on the vertical axis, P for probability. So you might have heard of a normal distribution or a bell curve, and that is something that looks a bit like this. A normal distribution is great for modelling things with small variations, for example, human height or shoe size. One thing you'll notice about a normal distribution is it is symmetrical. So that means that the thing where the probability is the highest, up here in the middle of the bell curve, I've drawn that slightly skew-whiff, but you get the idea. There's an equal probability of the actual measured value being lower or higher than that. A normal distribution is great when you have loads of independent random factors. They sort of add up to a normal distribution. But the thing that we're working with here, it doesn't work that way. With regards to time, the sort of duration of our cadence, it can't be negative. There is no such thing as having a cadence of -1 or anything like that. We've got a hard cutoff when you get to 0. And what people have found when modelling things that are related to time or duration or sort of frequency of occurrence over time, that kind of thing, is that there's usually a long tail of like rare, extended, large durations. They're not very likely, but they are possible. But of course, there can't be a long tail on the other side because of this fact that you can't go below 0. So what we want is a distribution that is skewed, that is asymmetrical. And so you might have a distribution that looks a bit more like this. That's called a gamma distribution, this one is, and is often used when you're modelling things with time and duration. There's in fact a special case of a gamma distribution is called an exponential distribution, and this looks like this. And you might ask, why did I not draw this sort of dipping back down to 0? This is because we're assuming that this keeps going up until it gets to 0 on the x-axis. And actually, the alpha and beta parameters I was talking about before, that's actually sufficient to model the skew and the variance of a gamma distribution. So that's one reason that we are storing things like that, because now we're working with something that other mathematicians have studied and can tell us how to work with it. So now let's talk about a thing called Bayesian updating. This is a formal sounding title for a concept that's not actually as difficult as you might think. All it means is you start with a prior belief and you are updating your belief based on a new data point that you've just been given. So in our case, our prior belief might be encoded in these alpha and beta parameters. That's enough to get our average and work out what we think the cadence of this task is at the moment. But we get a new piece of information. The user says, yes, I need to do this task now, to a review question. How do we update our prior belief? Well, the simple way to update alpha and beta is simply to add 1 to alpha and add the new duration to beta. And for the case of this model, that is Bayesian updating. There's nothing more we need to do. So now we have a term for it, but we don't need to do anything particularly complex at that point. Now, I mentioned that other people have already done some maths to help us get useful information out of a Bayesian updated model. We can get things like confidence. What that means is the model's made a prediction of what it thinks the most likely value is, but how confident is the model feeling? Not that it has feelings, but how confident is it in that result? If we've had hardly any data points, then the model might give a prediction but give it as low confidence. Whereas if we've had loads of data points and they all happen to be pretty much the same in duration, then the model will have a high confidence. This is the kind of thing that we can use existing maths to work out. So how does Deluge actually use this model? Do we simply compute the average and then wait that amount of time before asking the user the review question? No, let's lean into the Bayesian model and think of things in terms of probabilities. Let's start with making a probability threshold. So our probability, P, equals the early cost over the early cost plus the late cost. Now, what do these costs mean? The costs are essentially the penalty for asking the user the question too early or too late. These are constants. We hard-code these into Deluge, and using these constants, we can tune the model. We can skew things earlier or later as we see fit. And when we start beta testing this, we will take user feedback and tweak this model until it is giving the most accurate answers possible. Next up, we are going to need our running average. This thing I've mentioned before that's easy to calculate but is only one piece of the puzzle. And we're going to call that lambda. And it is simply alpha over beta, or beta over alpha, depending whether you want it in terms of the duration or in terms of the frequency. And finally, I can bring in a formula that will give us our optimal timing for the next time we ask a review question. And it's going to be minus log of 1 minus p over lambda. So what this equation is actually saying is, when will the next event happen, such as there's a p% chance that it actually happened before then? And the event, as you'll recall, is the ideal time when the task needs doing. And so we're going to use the output of this to be how long between task completion and us reminding the user, does this task need doing? So all our control here comes from these early cost and late cost weights. If the user says no to the initial prompt, if you recall, we need a shorter amount of time to back off by. And we can get that by putting different weights into the model calculation. We can put in a different early cost and late cost. and get a different number out that is skewed more in the early direction and therefore a lower number. I mentioned before about messy data and some of the other user inputs that we can use to try and account for that, such as the user saying, I've done this recently, and we handle that by faking inputs for the model. If the user says, I've done this recently, we treat it the same as if they said, I've done this just now, as in ticks a task off on completion, but pretend it's 2 days ago. And again, that number 2 days, we can tweak that when we find out how good our predictions are over time. One thing we're considering is adding a little bit of randomness to this prediction. And this is coming back to the fact that when the user says, yes, this needs doing, we don't know whether we've got it perfect or got it late. So by skewing randomly earlier by up to a couple of days, then we might teeter on the edge of the threshold a little bit more and get actually sort of more useful data sometimes. This will help the model start making accurate predictions sooner. And one other thing we do in order to get things started, when the user actually creates a blueprint that they've marked as smart repeat, we actually prompt them for a seed value, essentially, to the nearest order of magnitude, for how often they think this task will need doing. And we only give them a few options. It's like 1 week, 2 weeks, 1 month, 3 months, 6 months, a year. By having to choose one of those, that gives the model a starting point, and we then adjust this over time. For example, if the user's using it to predict the cadence for a task that's done yearly, then it will take a long, long time for us to get enough data points, given that we get around 1 a year, in order for things to converge to a precise, accurate amount. So by having the seed value at the start, it helps speed that up. So let's talk about testing. Doing computational tests on this model has been a bit hard for us because things are interdependent. The data that we get depends on when we present the review question. So if in our testing we are trying to work out how the model would predict something where the optimal cadence is 15 days, then we have to test it depending when we ask the user, as well as what changes the model makes depends on the user's response. So we've actually built a testing harness that can sort of account for this and runs the model, uses the model's output to work out what the next data point we're going to pass in as inputs will be. Obviously, actual human testing with real-world use would be great, but that takes a lot of time, especially for the tasks with a longer cadence. So Deluge is in the stage where it's got a few human alpha testers, but they've not been using it long enough yet to actually report back to me how well the smart repeat functionality is working. So I will get some of that information eventually, but I can't yet rely on this. And finally, I just want to talk about, will people use this? Will it be useful to people? Does this actually replace a scheduled repeat function? No, as I mentioned before, then some tasks make much more sense to model on an actual calendar schedule. Additionally, not every user will want to hand over full control, full trust to an app, certainly not at first, and some users might be happy to do that for things that are less important, whereas the things that are most important in their life, they might not want to use a system like this. So user preference plays a part in this as well. So yes, Deluge will have an actual regular scheduled repeat as well. And I will do a video talking about the interesting things with that at some point in the future. And as usual, please like and subscribe so that other people will watch my stuff, because doesn't everyone want to be an internet celebrity these days?